Esteemed viewers, in this tutorial we will continue with simple stress and strain. In the previous tutorial, you may recall that we defined as to what stress is, and we gave some practical examples where stress would come into play. And in this tutorial we will just probe little deeper into the stress and strain concepts. The basic stresses can be categorized into two types: the normal stress and the shear or tangential stress. Normal stress can further be broken down into two types. It could be tensile stress or it could be compressive stress. And shear stress can be divided further into a single shear or double shear, single shear stress and double shear stress. And normal stresses always acts perpendicular to the area of cross section or parallel to the axis of the member. It so happens that if we do not define or without set, any stress will be normally the normal stress. The normal stress will always act perpendicular to the area of cross section, or it will always act along the line of action of the applied force. And here is a member which is subjected to say a force going away, that is tensile force, and this is the area of cross section. We have taken a sectional plane over here and it is separated, and we have written the free body diagram of part 1, the part above the plane and the part below the plane, and this is the resisting area of cross section, and we can see the stress being developed in mutually opposite direction, and this stress when multiplied by the area will lead to F, and this stress when multiplied by the area will lead to F. Therefore the system is in equilibrium. However, you can notice the stress being placed away from the surface. Though they are perpendicular to the surface, they are away from the surface, and such a stress is tensile stress. Tensile stress will always try to pull the member, and stresses normal to the cross section or it will be parallel to the axis. Tensile stress will be developed in a member if the axial forces exert a kind of a pull on the member, something like this. This force is pulling this way and this force is also pulling this way. Therefore they should be equal to P. As far as engineering mechanics is concerned, the system is in equilibrium. However, when you take a section somewhere over here, you can see the stress coming to play, and which is equal to P by A, and this is a three-dimensional view of the stress system. Anyway, we cannot write very easily a three-dimensional stress system, and our problem solving procedure will become cumbersome. Therefore throughout the journey in this particular course, we choose to write a two-dimensional stress system. That means here this particular line connotes the area of cross section. And here is a machine called as universal testing machine, where specimens can be tested against tension. And here is a jaw of the machine. Here is yet another jaw. This works hydraulically, and this will just go down, and this will just go up. Actually, in this particular figure, this particular component of the machine will go down, thus exerting a kind of a tension force to this particular member, a rod. And there are two kinds of, depending on the material, whether the material is ductile or brittle. Some of the examples of ductile materials, as you must have guessed: gold, silver, copper, aluminum, steel. They are all ductile metals. And concrete, cast iron, some glass products or glass components, and high carbon steel, tungsten, they are typically brittle. When a ductile specimen or a specimen made out of ductile material like aluminum or mild steel is subjected to tension, at the time of failure it is going to form some kind of a neck, something like this, and it's going to break. When it breaks, when you see the specimens at a closer angle, you will find one of the part of the specimens form some kind of a cup, and the other forming some kind of a cone, so that they will be befitting each other when they are joined. And elongation will have something over here that is locally. As far as brittle fracture is concerned, it will break suddenly without any warrant, and it may go in an inclined way or it may go in a perpendicular fashion, but anyway there is no formation of cup and cone, and there is no neck formation as such. It will never give a clue as to when it will break. The breakage or the breaking of the specimen is almost catastrophic. It will come without any warrant. Compressive stress, on the other hand, will be generated within the material or within the component when there are two pulling forces, something like this. And when you separate the components, after taking a section somewhere over here, the stresses will be something like this. And you can see over here, and this is the stress, compressive stress, opposing this particular thing. And here, if you look at this free body diagram, this is the stress, compressive stress. When you join them, they will cancel away and the system will be in equilibrium. As long as this particular component resists, as long as this particular component is capable of sustaining the applied compressive force. Here also there are two kinds of failures depending on the material out of which the component is made, is ductile or brittle. For a ductile material, compressive stress pushes on the member trying to shorten it. The effect of tension is elongation or stretching, but the effect of compression is shortening. The ductile, as far as ductile materials are concerned, it's going to form some kind of a bulging. Okay, it will reduce in the height, that's right, but anyway there will be increase in the diameter. It will take some kind of a bulged shape. Okay, as far as brittle materials are concerned, you will see a crack in almost 45 degree, and it's going to break like this. The concrete specimen shown here will break something like this. As far as ductile material is concerned, owing to compression, it's going to form some kind of a bulging, lateral bulging. Somewhere here diameter is going to increase. This is a brittle failure. And there are some real world examples of components under tensile stress. And here is a bridge. This is called a suspension bridge, and this is the suspension, and this particular bridge is hung to this particular suspension. And these are all suspending rods. The suspending rods are in tension, and the suspending string is also under tension. And entire load of this particular bridge is borne by this particular string, of course a big diameter rope, steel rope actually, and this is the suspenders. And here is the cycle chain or the chain of a vehicle, automobile. This is also subjected to typical tension. Every joint over here is subjected to typical tension. And the nail cutter, and when you press this particular stud will be really raised, and this is going to raise this, and this particular stud will be subjected to tension. And as you could have guessed, this is the bow, and this is the string, and this is an arrow. In order to spring this particular arrow, you need to stretch this, and the bow as well as the string will be subjected to tension. And here is a wire to which a load is hung, therefore the wire will be subjected to tension. And remember the wires or ropes will always be subjected to tension. They can never be compressed because of their flexibility. And here a man is pulling this huge weight, and this particular thread he is using will be subjected to tension. And here the tug of war, both sides, this particular tug or this particular rope will be subjected to tension. These are all some of the typical mundane day examples wherein components are subjected to tension. Real world examples of members under compressive stress are here. The helical springs near the railway wheel, train wheel or bogie wheel will be subjected to compression. They will be taking the shocks, and when speed changes, it will be subjected to huge compression. And here this is the pier of a bridge, and pier of a bridge is the best example of a component, structural component, which will be subjected to compression. And here is a king post truss. A member, if it is wooden member and if it is subjected to compression, it is called as a post. And if it is made out of steel, it is called as stanchion. But anyway, compression member is a common name given to members which will suffer from compressive stress. And here, due to these particular loads, this member, and this member, and also this member and this member will be subject to compression, while the bottom member will be subjected to tension. Any member which is subjected to tension is called as a tie. Any member that is subjected to compression is called as a strut. Okay. Here it is a bowstring arch bridge, and this bowstring, just like looking like an arch, will be subjected to compression. And here the holders, the suspenders over here, column like things, will be transferring the load from the rod to this bowstring. Bowstring, due to its geometry, will be very good in taking compression, and this will also suffer from compression. These are all some of the real world examples. There is another kind of stress. Usually some of the authors will refer it as a different kind of a stress altogether. Anyway, it should be called as bearing pressure, and this is a category. Some authors do not mention about this, but anyway, bearing stress are compressive forces typically exerted on the external surface of a body or at the interfaces of different components of a system. And this kind of a pressure is also called as bearing stress. Bearing stress exists at the interfaces of two objects transferring the load. And here there is a column, steel column, which is receiving a load from a huge structures, let us say, and it is bearing against this particular base plate, thus making the load distributed over a big area. And this particular plate bears against this concrete footing. So the column bears against this plate, and this plate bears against concrete footing, thereby transferring the load, and at the interface remains what is called as bearing stress or bearing pressure. Bearing stress and bearing pressure can be typically seen in the real world example of the bridges. Bridges are usually supported on bearings. They are called as typically bridge bearings, and at this interface there will be huge bearing stress. And this bearing stress will become a compressive force or compressive stress that will be transmitted to the pier beneath. Shear stress. This is the second kind of a stress. The stress developed tangential to the surface or area of cross section. Resistance developed tangentially or parallelly to the unit area of cross section. Here is a component. To this component there is another component attached, and we need to, for some situation, for some requirement, let us say we need to transfer the load over here, and if at all it fails at this particular junction. And here there is a lot of shear stress that is being developed, and this is the resisting area. Okay, and shear stress is also given by force or shearing force, that means this one, divided by resisting area. This is the area, and when the load is applied, it's going to the stresses will be developed like this, and at the time of failure it's going to just get detached from the parent component, and this is how shear failure will take place. And you can see over here the shear stress will be developed parallel to the area of cross section, and this is the resisting area. If the force is acting like this, it will oppose this force internally. And this is analogous to or akin to the friction that you studied in your engineering mechanics subject. But anyway, friction is external, but shear is internal to the material. And aftermath of the failure is some kind of a roughening of the surface and some kind of a residue that will be left over the surface. Okay, and there are some real world examples of shear force and associated stress. When we cut a vegetable with the help of the knife, we are actually imparting shear force, and this onion is resisting this particular shear force applied through this knife by shear stress. And here the scissors, when we cut something with the help of the scissors, and at the interface here, at the cutting plane, it is only shear which is doing the magic of cutting this particular tape into two pieces. And this is a typical failure again. This is a joint, dovetail joint, and the force is applied over here, and it's going to get loosened at this particular joint due to shear. And this is a rotating blade, and it is immersed in water. There will be a lot of shear stress, that is being shear force, and therefore shear stress developed on the surface of this on the surface of this fan, on the surface of this wings of the fan. And here when we cut a vegetation with the help of a knife, actually the magic is done by transferring the shear force, therefore by generating some kind of a shear stress in the stems of the plant. And shear stress can be seen in two forms. It could be single shear or it could be double shear. In single shear, the shearing force is resisted by a single area or lone area of cross section. Here is a column, here is a beam which is getting attached due to this L-shaped fastener, and here is a rivet and here is a rivet. If the system breaks, these two, this rivet number 1 and rivet number 2 will be into two pieces. Therefore, only single area participates in taking the shear. Therefore, such a situation will call for single shear. And here is another example. This particular plate and this particular plate is attached through this particular nut and bolt system, and when this is pulled excessively, this stud of the nut and bolt system will be broken into two pieces, and it fails exactly at this particular interface. Therefore, only one area of cross section participates in taking the load. If we have applied force F over here and F over here, and the shear generated over here in the area of cross section of the stud will be equal to F by A. And here this is the typical scenario of the failure. This particular portion of the nut has come this way, and this has given this way. There is a hole that is being created. This is the plan of this particular system. Here it is a plate, a lap joint is getting pulled by P, and it has a width of 110 millimeter. When it is pulled, if the plate fails, it will fail due to excessive tension. It is called as tearing around the stud. And if the stud is weak, it's going to fail in single shear, because it will be only one area of cross section over here is participating in taking resistive in developing the resistance over the area against this particular force P. Double shear, on the other hand, will be appearing in some of the fasteners where there is a situation of double area, that is two areas of cross section participating in resisting the forces. The shearing force is resisted by two areas of cross section. Here is an arrangement. There is a force that is getting pulled, and here is a pin which runs through the heart of this particular joint, and if it breaks, it will be into three pieces. Here is one area of cross section, here there is another area of cross section. Therefore, if this were to be P is resisted by two areas of cross section, and if area of cross section of this particular pin is A, then the shear stress here should be P divided by 2A, and at the time of failure it will be something like this. And there could be a situation something like this, where a force is applied at this end, force is applied at this end, and force is applied at the center. If that is the situation, though it breaks into three pieces, though it is double shear, there is also bending. Therefore, such a situation is called as it is not a situation wherein we can just say there is a pure shear. Okay, along with shear, another deformation will also take place. That is, another deformation will also occur, that is bending of this particular stud system. So here tau equal to P by 2A, one area of cross section here, another area of cross section over here. And stress on a bolt, double shear, and here is a plate which is getting pulled like this. Automatically it will generate reaction over here, Fs. So Fs is over here on this particular area, Therefore, Fs plus Fs, 2Fs will become F. Therefore Fs by A, area of cross section. So it is half F. Here shear force as far as one plate is concerned is half F divided by A. Or directly we can place F by 2A. Here is one area of cross section where probably a failure can happen. Here there is another area of cross section where probably failure can happen, and here it is shown in red. This is the area of cross section, and this is another area of cross section which is participating in resisting the shear force F. Right. Then deformation due to axial stress. There can be two types of deformation that may happen due to axial stress, and this is pulling. So this is subjected to, this particular component is subjected to tensile stress. Or right, this is also pulling. The spring is subjected to tensile stress, and here we are compressing. The ball is subjected to compression, and here this is also getting pulled, and the threads over here, the wires over here will be subjected to tension. And if this is the component of length L and this is the force P applied, this will get elongated due to tension. And if this is the original area length, original length L, and this is change in length, some kind of increase in the length, and it is so small, that it cannot be measured actually. We need electronic measuring devices in order to precisely measure such a small quantity. Therefore it is designated as DL, small change in the length, small increase in the length. If we happen to refer this relatively, we will have strain, and we will get the strain. When deformation is accounted, it will become strain. When deformation is referred relatively with respect to original dimension, it becomes strain. So here strain is normal strain because it happens perpendicular or along the longitudinal axis. Here it is getting compressed, and this is the reduction in length. In compression there is reduction in length, however small it may be, and in tension it is increase in the length, and the length increase happens to be very, very small. Therefore it is denoted as DL and DL. And there are two types of strains actually. Normal strain is represented by epsilon. It is DL by L, change in length by original length, change in original dimension divided by original dimension. Since the length of the component happens to be in meters, okay, and the change in length happens to be a fraction of millimeter, we will also convert this particular length into millimeter. Therefore this is millimeter by millimeter. Millimeter and millimeter will get cancelled away. Therefore strain is a unitless quantity. It is very, very small, very, very small. For this particular example, if we expect the change in length to be 0.5 millimeter, and if the length happens to be 5 meter, then it will be 0.5 divided by 5000 millimeter. Okay, therefore strain will be usually very, very, very less. But in order to cause such a small strain, it would have consumed huge stress. So it is very important to remember it requires huge amount of stress, particularly in metals, particularly in concrete, which are very strong materials. Okay, the strain is going to be very timid, strain is going to be very meek. But in order to create such a meek strain, it requires enormous amount of stress. For example, steel will be subjected to a small strain of let us say 0.5. If it is mild steel, by that time it would have taken around 320 Newton per millimeter square of the stress. 320 Newton per millimeter square is equivalent to placing 320 apples one above the other, or expecting such a kind of a force over an area measuring 1 millimeter by 1 millimeter. This example is given so that we should get some kind of a feeling for this figure, how small the strain is, and it is a unitless quantity. It's a relative quantity. Okay, so a small change in the dimension divided by original dimension. So with this definition, we can also define other kind of strains, right, as a secondary strain. That is lateral strain. Lateral strain is let us say change in diameter by original diameter. Change in diameter by original diameter. Change in diameter is dd. Let us say when it is pulled, the diameter is going to reduce. If length is going to increase, diameter is going to reduce. So a change in diameter, which will be very, very small, lateral dimension, change in lateral dimension divided by original lateral dimension. Change in lateral dimension is dd and original dimension is d. This will become lateral strain. Similarly, in the same token, we can explain for other metals also. Okay, it could be dt by t, change in thickness. It could be db by b, change in width, or lateral strain of the width, lateral strain undergone by the thickness. Therefore, having said that strain is a very small quantity, often the word strain in mundane life is used as a misnomer. We say, often we exclaim, I am strained terrifically. And as the magnitude of the strain is too small, it is illogical to call strain to be terrific. Thus, it is rather logical if one says, I am stressed terrifically, because stress is a huge quantity. In the same breath, it is wrong to say that the component is subjected to terrific strain, because strain can never be used to connote a force. Strain can never be used to connote a force, because strain is a very, very, very small quantity. There are basic strains, normal strain, which happens along the length. It's also called as longitudinal strain. It happens, the direction of the movement will be along the length, but perpendicular to the area of cross section. So therefore epsilon over here is delta L by L, and this is delta L, change in length, and original length is the length of the specimen. Lateral strain could be dd by d, if at all you want to measure the strain along the diameter, change in diameter by original diameter, change in thickness by original thickness, and change in width by original width. Okay, and they are also called as linear strains. This is linear strain, they are lateral strain. Lateral strains would occur for the lateral dimensions of the specimen or the component, and the longitudinal strain or normal strain will occur along the length. Length leads to longitudinal. And here is a example. Here is a bar or a strip of iron or a bar made out of iron. It is subjected to F, and the original dimension is B1 width and T1 the thickness. Okay, after the stretching B1 should reduce, T1 should also reduce, the length should increase. Okay, increase in one direction, or the increase in strain in one direction will always lead to the decrease in strain in other directions, in the lateral direction. So B1 will get reduced, T1 will get reduced, only length will get increased. So it is B2, let us say, after the application of the load, B1 will become B2, little reduced, and T1 will become T2, little reduced. Now T1 minus T2 will be dt, B1 minus B2 will be dB, and if we take the ratio, we will get lateral strain. There is yet another strain called as shear strain. So we have gone through three kinds of strains: the normal strain, or linear strain, or longitudinal strain, then lateral strain, the strain that would occur for the lateral dimensions. The third category is shear strain. You consider a component, and for some reason you are applying the force like this, and this particular portion is fixed, and this particular portion is being pulled like this. Therefore, it will sway. It will move in this particular direction. And some kind of an angular deformation will happen. This angular deformation is called as shear strain. While the other kind of strains are linear in nature, the shear strain will be angular in nature. There will be total deformity. There will be total deformity. There will be total disfiguration. The shape of the body will change if a body is subjected to shear strain, shear stress. Therefore, due to shear strain. And here is a cube. The force is applied like this, and here also force is applied like this. It's going to sway like this, and this angle is shearing strain. Phi, let us say phi. And here is yet another example. There is a cylinder. For some reason you are applying the force like this, and this end is fixed, or this end is subjected to force F. Therefore, it will be in equilibrium. This F and will cancel with this F. Okay, the engineering mechanics principles are complied with. But anyway, however, it is subjected to some kind of a sway. This sway is represented by this angle theta, and this is very, very, very small, and this is called a shear strain actually. In order to account for this shear strain mathematically, and let us say this is a cube, this is a sponge of height, let us say 0.1 centimeter, and if there is due to some force, if there is a sway of 0.02, okay, this one delta x is 0.02, then shear strain is actually tan theta. Tan theta is opposite by adjacent. Opposite is delta x, adjacent is L. Therefore, tan theta, since this theta is very small, tan theta can be taken equal to theta. Therefore, tan theta equal to 0.02 divided by 0.2 into 10 to the power of minus 2. Okay, 0.02 divided by 0.1, or you can directly write this 0.02. Okay, the dislocation, the distance, the change in a point, this is the point, now it is over here due to application of the shear. Therefore, this is the magnitude of dislocation with respect to the height. If a normal strain is referred as change in length by original length, shear strain is always referred as a ratio of magnitude of dislocation of a point with respect to the standard height or unit height. So therefore, this is the ratio is opposite by adjacent. 0.02 divided by 0.1, it becomes 0.002. So therefore, we have taken to understand that shear strain is going to be a very small quantity. There are three kinds of strains. One is normal strain or linear strain, longitudinal strain, and the second category is lateral strain, which will happen to the lateral dimensions like diameter, width, or thickness. And there is the third category of strain is shear strain. And with this, we close the second version of our tutorial. And if you have liked it, kindly subscribe to my channel. And until I come back with tutorial number 3, which again discusses on fundamentals of simple stress and simple strain further. Until then, bye. Thank you.